This video is one in a series that explains how to use the program Comprehensive Meta-Analysis. The previous video looked at how to enter data. In this case, we're going to look at how to run a basic analysis. This video works with the example of means. There are other ones that use examples of proportions or correlations. I'm going to use the data set that we set up in the previous video. This is the data set based on the first 6 studies, and it corresponds to the data set that we have in the book Introduction to Meta-Analysis. At this point, we've entered the data for the 6 studies. The program shows me the corresponding effect size as Cohen's d, as Hedges g, and as the raw difference in means. I'd like to use Hedges g as the primary effect size, so I'm going to right-click someplace in this area over here, and the program says set the primary index to g. I'm going to select that. I can save it, so that's going to be the primary index the next time I open up the study as well. I go to run analysis, and the program shows me this basic fixed effect analysis. I have over here for each study the study name, Hedges g, the standard error, the variance, the lower and upper limit, the z-value, and the p-value. The program shows me that both in numbers and also as a forest plot. So for example, for the first study, the effect size is 0.095, let's say 0.10, with a confidence interval that goes from minus 0.26 to plus 0.46. As always, if the 95% interval includes the null, includes 0, then the p-value is going to be greater than 0.05. In this case, the interval does include 0, so the p-value is 0.60. In this example down here, the confidence interval does not include 0. The p-value is less than 0.001. If I click on this button up here, the program shows me the relative weight assigned to each of the studies. This study, for example, gets about 40% of the weight in computing the combined effect size. This study over here gets about 8% of the weight in computing the combined effect size. And down here we see the combined effect size, the summary effect. The effect size is 0.41 with a confidence interval that goes from about 0.30 to about 0.54. It does not include the null, and therefore it follows that the p-value is significant. In this case, it's less than 0.001. All of this is done using a fixed effect model. I can come down here and click on the word random, and now the analysis is done using a random effects model. And by the way, the basic idea of a random effects model is going to be that the studies are going to get more even weights, so that under a fixed effect, you can see that there's this major difference between this study and this one. Under random effects, that difference is moderated. Under the random effects model, the study gets 23% of the weight. The study gets 12% of the weight. Down here, the effect size has now shifted so that it's 0.36. With the confidence interval, it goes from approximately 0.15 to 0.56. And you can actually show both models at the same time. If I click down here on both models, this is the fixed effect synthesis. This is the random effects synthesis. You'll notice that in this particular example, the fixed effect estimate is 0.41. The random effects is a little bit smaller. It's 0.35. That is not necessarily going to be the case in any meta-analysis, although the two will generally be different. There's no reason to expect that either one is going to be the one that has a higher effect. On the other hand, the confidence interval here is wider than this one, and that is generally going to be true. You can see over here the weights assigned under the fixed effect model, the weights assigned under the random effects model. And as I said before, under the fixed effect model, the big studies get a much larger chunk of the variance. The small studies get a much smaller one. Under the random effects model, that's all moderated. The study which previously had 40% of the weight under fixed effect is now knocked down to 23% under random effects. By contrast, the study which had 8% under fixed effect is bumped up to 12% under the random effects. These weights also allow you to understand why it is that the effect size in this example goes down as we moved from the fixed effect to the random effects, it is because this particular study, which happens to be the largest study in our sample, under the fixed effect model it got about 40% of the weight, so it took the effect size and pulled it to the right. By contrast, when we move to the random effects model, this study is getting only about 23% of the weight and therefore has less of a pull on the effect size. And for that reason, the effect size shifts back more towards the consensus, if you will, of the other studies. So that's a very basic look at this at the analysis. Let me show you a couple of more things that you can do over here. You can click on this button which says Next Table, and you're going to see largely the same kinds of information. First of all, under the fixed effect model, we have the number of studies, the point estimate, standard error, variance, lower and upper limit, the z-value, and the p-value. So everything in this area relates to the test of the null hypothesis and the estimate of the mean effect or of the common effect. We see the same information for the random effects model, the number of studies, the point estimate, standard error, lower and upper limit, z-value, p-value. Okay. Then we move over to this section over here, and whereas everything over here dealt with tests of the mean effect or of the common effect, now we're looking at the heterogeneity. The q-value is 12 with 5 degrees of freedom and a p-value of 0.035. This looks at the question of whether or not the dispersion and effects that we're seeing is consistent with the idea that all of this heterogeneity is just due to random sampling error, or whether it is more likely that some of this is due to real differences in the effect size. Or let me put this another way. Let's say that every one of these studies had an infinite number of people in it, so that each one reflected the true effect for that particular population. If all of these share a common effect size, then once we get rid of all the sampling error, we would expect all the effect sizes to line up exactly in a column. On the other hand, if the true effect in each study is somewhat, if the true effect in each study varies, that, for example, the true effect in one study might have been a G value of 0.4, and another one it might have been 0.3, and another one it might have been 0.5, because of various reasons. Maybe the populations were a little bit different, or the intervention was administered in a somewhat different way, or the outcome was measured differently. In that case, if we got rid of all the within-study sampling error, we would expect to see some variation in the effect sizes. Well, that variation is addressed by a number of statistics. The first one is the Q statistic, which is really the sum of squared deviations, which turns out to be 12. Then we have degrees of freedom, and then we have a p-value, which is 0.035. And that tells us that it's a test of significance. It says that it's unlikely that the amount of dispersion that we're seeing over here would be due purely to within-study sampling error. That it is more likely that at least some of the dispersion that we're seeing is due to real differences in the effect size from one study to the next. To put that more formally, if in fact all of these studies share the same true effect size, then in only about 3 times in 100 would we expect to see this much variation from study to study. And this Q statistic and this p-value are based both on the amount of dispersion that we're seeing and how precise each of these estimates is. So that if each of these studies was very small, we might expect to see a lot of dispersion just based on random error. But if each of the studies is relatively large, so that each of the estimates is relatively precise, then we would expect to see less dispersion based on sampling error. So the Q statistic that we're looking at takes account of how much sampling error we would expect based on the size of each study, based on the variance of each estimate, and then looks at the observed amount of error and asks whether or not the observed amount can be attributed purely to sampling error. In this case, we're saying that it probably is not. I-square is another measure of heterogeneity, but it's measuring something else. First of all, it's based on the Q statistic, so the same p-value would apply. But I-square says, of this dispersion that we're seeing, what proportion of that dispersion is probably based on real differences among the studies, and what proportion of it is probably based simply on sampling error. Or to put it another way, if each of these studies was large enough so that it estimated the effect size in that study very precisely, how much of this dispersion would disappear and how much of it would remain. And the I-square statistic says that about 65% of it would remain and about 35% of it would disappear. So these estimates would come closer to each other, but we would still see about two-thirds of this dispersion would still remain. And the next statistic we have over here is tau squared. Basically what that's doing is it is quantifying the variance of the true effects. In other words, we could go back in, take these effects, ask how much they vary one from the next, and compute the standard deviation of those effects or the variance of those effects. But that would not be a useful thing to do, because the variance that we're seeing over here has two parts to it. Half of it, or I'm sorry, a part of it is just random sampling error, which we don't care about, and part of it is true differences from study to study. It's the true differences from study to study that we're interested in. We would like to know, if we got rid of the sampling error, how much would these studies vary? What would the standard deviation of those effect sizes be? What would the variance of those effect sizes be? Well, the standard deviation of those effect sizes, of those true effect sizes, is called tau, and in this case it's 0.193, and it says that if we replace these observed effect sizes with what we expect are the true effect sizes, that the standard deviation of those effect sizes would be about 0.19. And the variance of those effect sizes would be what we call tau squared, and that would be 0.037. And 0.037, the variance turns out to be an important quantity because that's used in assigning weights to the random effects model. And the standard error and the variance, this is the standard error of tau squared and the variance of tau squared. It tells us how accurate this estimate of tau squared is. The p-value for tau squared is the same p-value as the one for q. This is whether or not we can reject the idea that tau squared is 0. One question that often comes up is, why are these statistics over here, tau squared, for example, the q statistic, are presented on the line for the fixed effect model? And people ask, well, where are these statistics for the random effects model? Well, the answer is these statistics over here are computed based on the fixed effect weights, but then they apply both to the fixed effect model and to the random effects model. Because they are computed using the top row, but then are applied to the bottom row, some people prefer to see them attached to the top row where they're computed. Some people prefer to see them attached to the bottom row where they are applied. We chose to put them on the top row because we just thought that was a little bit clearer, but it's really a judgment call. But in any event, whether you're working with a program that puts them at the top or the bottom, it is always the case that they are based on the fixed effect weights and they are applied to the random effect weights. And what I mean by that is that when you go to compute Q, and then from Q you derive tau square and I square, that's always based on the weights that we see in this column over here, the fixed effect weights. By contrast, when you go to apply them, under the fixed effect model, we are asserting, as a matter of fact, that all of the true effects are exactly the same. And therefore, in a sense, we are asserting that tau square is 0, and that I square is 0, that none of the observed variation is true, and that the variance of the true effects is 0. And therefore, these numbers really have no meaning. Where they do have meaning is when we use them to compute compute the weights for the random effects model, and to explain the random effects model by saying, for example, that a certain percentage of the variance that we're looking at is true, or to talk about the actual dispersion of the true effects. All of that only makes sense in the context of a random effects model. Okay, let me come back over here by clicking Next Table. I'm going to simply work with the random effects model for now, so I'm going to come down here and click on Random Effects. At this point, you know pretty much how to use the basic analysis, but let me show you a couple of more things for those of you who are interested. Okay. Over here we have the weights. These are actually the relative weights, 23% of the weight. 23%, when computing, excuse me, when computing the combined effect, this study gets 23% of the weight, this study gets 12% of the weight. If I right click over here, I can say show raw weight, and we actually see the actual weight, not the relative weight, but the actual weight being assigned to each study. The way that I like to think about the weights is the weight represents the total amount of information included or being that comes from each study. So as the weights get larger and larger, the estimate becomes more and more precise, and this confidence interval is going to get more and more narrow. By contrast, the relative weight explains the relative impact of each study. So if you look at the relative weights, it's the study that has a higher relative weight that is going to have more of an impact on this point moving to the right or the left, but it's the raw weights that are going to have an impact on how wide the confidence intervals are. Something else that we can do over here is we can say scale relative to the maximum, which means that these bars are simply going to be pulled out a little bit more so that the distinction between the larger studies and the smaller studies will be more obvious. I'm going to get rid of the raw weight. I don't need that right now. We can click on this. We can click on this, and the program is going to show us the residual for each study. In other words, how much that study differs from the overall effect. People sometimes find this is a helpful way to identify outliers, so that, for example, any study that has, for the sake of argument, a standardized residual of greater than 1.96 is a study that falls outside what you would expect to be the confidence interval for the mean. It doesn't necessarily mean that the study is wrong. It certainly doesn't mean that the study is wrong, but it does help you pull out studies that you might want to take a closer look at. It also is a good way of identifying studies where you might have had a mistake in the data entry, and so it's useful for that as well. I'm going to hide the residuals. What else do we have over here? Show or hide counts. Okay, so what we have over here is the sample size for the treated group and for the control group, and I can right click on that and I can say show the total in each study. And this is actually useful because you can see that the studies with the larger sample size are going to be the ones getting more weight in the analysis, certainly when you're using the fixed effect analysis. To be clear, the weights are based on the variance, not simply the sample size, but generally, especially when we're working with means, there's the sample size is pretty closely related to the variance. And I'm going to get rid of this. Okay, over here we can customize the statistics so that, for the sake of argument, if I didn't want to show the standard error and the variance, I wanted just to have hedges G and the p-value, I could do that. And then you also, let me just bring those back because I think they're useful. I'm going to click show all of them. You also can set the number of decimal places, and you can do that for each of these separately, or maybe you want to just have more decimal places for p-values. I don't have a lot of, I tend not to focus on the p-value, but just to show you how this works, I could take the p-value and say that I wanted to display 6 decimal places for it, and you see how that works over here. Let me bring that back and say that I want to do that automatically. and click OK. Something else that we can do, there's something here called one study removed. As we're looking at this now, this is the overall estimate of the effect of the estimate across all the studies, and the line that we see over here reflects this study, this line reflects this study, and so on. If I click one study removed, then basically every one of these rows is an estimate based on all studies except this one. So for example, this estimate over here of 0.411 is the effect size that we would get in yellow if we did an analysis based on all of the studies except for Carroll. And this is an estimate of the overall effect based on all of the studies except for Grant. And the reason for this obviously is we can see, well, pretty much omitting any single study is not going to matter a lot. The overall effect that we got was 0.35, and if we omit any one of these studies, this, or this, the effect is going to be pretty close to 0.35, with one exception, which is this one. If we left out this study, the effect would drop from 0.35 to 0.25, which is a pretty big difference. And so that's so we can immediately identify this, and you say, well, the study had a pretty large impact on the overall effect. If we were doing this using the fixed effect model, the difference would be even larger. The overall effect was 0.41, and if you left this study out, it would go to 0.25. Let me go back to the random effects model for a minute. Let me just to show you how this is working. What I'm saying is that the overall effect is 0.35, but if we leave out this study, it goes to 0.25. Let me go back to basic stats, and let me actually leave out this study. And to do that, the study is Donut. I'm going to right-click over here, and I'm going to say select by study name. I'm going to get rid of Donut. I'm going to run the analysis, and you can see that the overall effect is now 0.255, exactly as advertised. Let me come back over here, and let's say select all, and put that study back into the analysis. Something else that we can do over here is a cumulative analysis. Again, under the basic analysis, the basic stats, every one of these lines represents the information for that study. If I click on cumulative analysis, the program does an analysis based on the first study alone, on the first two studies, on the first three, and so on. So when we come down to the very end, the overall effect that we're getting is the same as we had before. But this tells us what the effect would have been if we looked at it when only the first study had been completed, the first two, the first three, and so forth. And so it shows the shift of the evidence over time. Or let me put this more clearly. If we had sorted the studies by year, then this would show the shift of the evidence over time. In this case, the studies were simply sorted. There was no particular order to them, so this is not terribly meaningful. But in some cases, when we do want to look at the shift of the evidence over time, it's going to be a very powerful tool. And we don't need to look at the shift of the evidence only by time. Let's say, for the sake of argument, that we had sorted these studies by some measure of how of study size, so that we have the large studies at the top, which we think are more reliable, and then we have more studies added towards the bottom, which are smaller, and we can see if the effect shifts as we move from the larger studies toward the smaller ones. And so this can sometimes be a useful tool. You'll notice over here, by the way, that the weights are the cumulative weights, so that using this as 100%, we see that after we've added the first study, we now have used up basically 15% of the information that we had, after the first two, we've used about 32% of the information, and so on down to the bottom where we now have incorporated 100% of the information. I'm going to come back over here and click on Basic Stats. There's a final tab over here called Calculations, and what this does is it opens up a window on the calculations that were used to compute the effect size and the other statistics. So for example, for the first study, for Carroll, the point estimate is 0.095, which corresponds to the G value for that study. The variance is 0.033. If we come back to study entry, you'll see that the variance over here is 0.033. That's where that number comes from. Toss square, let me click on random effects. Tau square is 0.037. This is the variance within studies. This is the variance between studies. The basic idea, again, is that we're asking how accurate, if we come back to the main screen, we're trying to use each of these studies to estimate the overall mean effect. And the error in, let's say, using this study, the accuracy of this study as an estimate of this depends on two sources of error. One is the within study error, the fact that this estimate is not a fully accurate estimate of the effect in this population. And the second is the between study error, the fact that even if we knew this effect size exactly, that this effect size is not the same as the true mean effect size for all possible studies. So those are two sources of variance, within studies and between studies. So if we come back over here, this is the variance or the error within studies. This is the error across studies, 0.037. And just to remind you, if we come back over here, 0.037 is the number that we saw for tau squared. This is the total variance. It simply means that we are taking the sum of the within study variance and the between study variance, 0.033 plus 0.037, gives us a total variance of 0.07. And then the weight is going to be the inverse of this. So 1 divided by 0.07 gives us 14.23, which is the total weight assigned to that study. If we come back over here to the basic statistics again, and we click on weight, and we say show raw weight, that study is getting a weight of 14.23. Come back again to the calculations. That's the weight. W is simply the weight. In this case, it's going to be the same as the IV weight. T times W is the weight times the point estimate, so 14.23 times 0.095 is 1.35. T squared times W is the point estimate squared times the weight. These are simply numbers that are used in the calculation. They are all explained in great detail in the book. And over here we come out with a sum for C and Q and DF, all of which are used for computing tau square. And you can review all of that in the book. The key numbers that we take out of this is the sum of the weights is 90, and the sum of the weight times the point estimate is 32. If we take 32 divided by 90, we're going to get the overall effect size, which is 0.358. And if we take the sum of the weights, 90.284, and take 1 divided by that, we're going to get the variance of the effect size, which is going to be 0.011. We take the square root of that to get the standard error of the effect size, which is 0.105, and then we can compute the lower and upper limit and the z-value and the p-value. So that was a quick run-through of a basic analysis. Let me see if I forgot anything. There's always the tutorial over here, so you can highlight that and then just sort of walk through this. It will explain to you pretty much what I just explained now, but it's nice to have that if you're using the program someplace and don't have access to the video. That'll walk you through everything. In the next video, I'm going to show you how you can take what we see over here and create a high-resolution forest plot. And then in later videos, I'll show you how to do such things as subgroup analysis, regression, publication bias, and so on. Bring us back to the main screen, save the study. Thank you very much for your attention. Our website is www.metaanalysis.com.